All right, here's another word problem that we're just going to walk through together. We start off again. Let's read the problem. A baseball is dropped off a bridge. Again, that's code for the initial velocity is 0 because, again, it's motionless. You release it, so it's not starting with any speed. How far will it travel? That means that we're looking for a displacement, delta x. After 4 seconds, that's our time. And again, this is not enough information to solve the problem at this point. We're going to also need to know the acceleration. We're going to make the assumption that we're on Earth, and therefore the acceleration is 10 meters per second squared. Again, we're rounding our 9.8. And the reason I'm choosing this to be positive is because something is being dropped. It is going only in one direction. So if something is only going in one direction, it's much easier to keep all our numbers positive. So that's the simple explanation for that. So we're looking for delta x, so we're going to go through our equations and find the one that has delta x and these other variables. So 1 and 2 are out because they require average velocity, which we don't have. Equation 3, let's see, we're looking for delta x, not even in equation 3. And equation 4 has delta x, it has vi, it has t, and it has a. That's good. Equation 5 we can't use because we do not know vf. So now we're just going to go through and we're going to plug in our numbers. Again, all our units seem to match up. Seconds, meters per second squared. They're all the same type of unit, so this should work. So now we're going to solve delta x equals, so vi, which is 0, times t, which is 4, so 0 times 4, plus 1/2 times a, which is 10, times t squared, 4 squared. Now be careful here, a common mistake people make is they square everything. You're only squaring the 4. So that means delta x equals 0 times 4 is 0. So it's just 1/2 times 10 times 16. That's what 4 squared is. And then 1/2 times 10 times 16. So if we do that out, it's going to be 80. So 80 meters is our displacement. So in the course of 4 seconds, this rock will fall a distance of 80 meters. And that's basically that problem right there. Here's another problem. Again, we're going to walk through it. A volleyball is thrown upward at a speed of 15 meters per second. So that's our initial velocity. I'm going to write VI is 15 meters per second. And it wants to know how fast it's going after 2 seconds. So time is 2 seconds. And we want to know the speed at the end of that 2 seconds. So we're looking for VF. VF does not necessarily mean when it hits the ground. It means later on. So we can say later on is whenever we want to. In this case, it's after 2 seconds. And again, we're going to need the acceleration. This one's a little trickier. The ball is thrown upward at a speed of 15 meters per second. However, gravity pulls the ball downward. And so they're opposite directions. So unlike when the rock was falling and everything was in one direction, here we actually have to be careful and pay attention. If gravity pulls in the opposite direction and we're saying that it's thrown upward and that's a positive velocity, then that means that the acceleration is going to have to be negative in this case, so negative 10 meters per second squared. So we can do this all as before, but we just have to use that negative number for a. So what equation are we using here? Well, again, I'll skip through. It's going to end up being equation 3 because we're looking for VF and we have everything else in there. So VF is unknown. You know, VI is positive 15. I don't have to write the plus. I'm just trying to make it obvious. Plus negative 10 times 2. So basically 15 minus 20, or negative 5 meters per second is what VF is. So what does this mean? Well, if its velocity is negative 5, it means that the volleyball is now falling at 5 meters per second because we defined a negative as going downward. So you could say it's 5 meters per second downward. And that would be kind of a word answer to this without just putting a negative number. So that's the final answer to this problem. So anyway, that's about it. Until next time, I am Derek Genova. Have a delightful day.